Welcome back to machine learning. This video will cover reinforcement learning. The topics in this video are inspired by and portions are borrowed from Andrew Ng's Part 13, Reinforcement Learning and Control, from his CS 229 lecture notes. What is reinforcement learning? Reinforcement learning is a huge topic that would require an entire course to cover in detail. We are covering it in one video, so this will not go into the state of the art or anything like that. I want to give you an overview of reinforcement learning so you understand what it is and how it works at a high level. Reinforcement learning is how most learning is done in the real world by people. Think about a baby learning to walk. There's not a right or a wrong way to do it, and there's no specific feedback that can be given to produce a result of walking. Instead, there are little movements and so-called rewards. We are rewarded when we stand up and when we step forward. We receive negative rewards when we step backward and we fall. These rewards are in the form of progress towards a goal and external rewards. Positive rewards come in the form of encouragement from family and progress towards a goal, and negative rewards come from hurting ourselves when we fall. In a reinforcement learning scenario, we want the learning algorithm to identify how to choose actions over time so as to maximize rewards. We will start with a Markov decision process, which is the formal framework on which RL problems are usually posed. A Markov decision process is a tuple with S, A, P sub SA, gamma, and R. S is a set of states. For example, in an autonomous helicopter flight, S might be the set of all possible positions and orientations of the helicopter. A is a set of actions. For example, the set of all possible directions in which you can push the helicopter's control. PSA are state transition probabilities. For each state, S, and each action, A, PSA is a distribution over the state space. We'll talk more about this later, but briefly, PSA gives the distribution over what states we will transition to if we take action A in state S. Gamma is called a discount factor, and it's a value between 0 and 1. R is the reward function. It takes inputs of states and actions and produces a reward. Rewards are also sometimes written as a function of state S only. Remember automata? Remember finite state machines? This is basically what a Markov decision process looks like. We will start in some state S0, and we get to choose some action A0 from A. As a result of our choice, the state transitions randomly to some next state S1. This S1 is drawn from PS0A0. Then we get to pick another action, A1. As a result of this action, the state transitions again, now to some S2, which is drawn from PS1A1. We then pick A2 and so on. Upon visiting the sequence of states S0, S1, and so on with actions A0, A1, and so on, our total payoff, or reward, is given by this expression here. We have our reward at time 0 plus gamma times our reward at time 1 plus gamma squared times our reward at time 2, and so on. We can also write this as a function of the states only, in which case the equation would look like this. We're going to be mostly working with the simpler state rewards, but generalizing to RSA is not challenging. Our goal in reinforcement learning is to choose actions over time to maximize the expected value of the total payoff. This E here is the expected value, and inside these brackets is the total payoff or reward. What is gamma doing here? It's being discounted by a factor of y to the t, where t is the time step. So we want to accrue positive rewards early on as they will have the largest impact. A policy is any function pi that takes inputs from S and produces outputs from A. That is, it takes a state and produces an action. It's a mapping from states to actions. We say that we are executing on some policy pi if whenever we are in state S, we take action A according to that policy. We also define the value function of a policy according to this equation. What does this even mean? Well, this V pi of S is the expected sum of discounted rewards, given that we start in state S0 equals S, so we start in state S, and we're making choices, that is, taking actions according to some policy pi. The notation's a little bit clunky, but in English it's just the value function is the expected sum of discounted rewards, given that we start in state S and we take actions according to the policy pi. Given a fixed policy, pi, its value function satisfies the Bellman equations. There's nothing to be worried about here. This just has to do with dynamic programming. All it means is that we're actually going to be able to do some interesting things with it. This is a huge change. What is even going on and why do we need it? This just says that the expected sum of discounted rewards for starting at S consists of two terms: the immediate reward at S and the expected sum of future discounted rewards. The Bellman equations come from optimization using dynamic programming, and they can be used to efficiently solve for V pi. In a finite state Markov decision process, that is, there's a finite number of states, we can actually write down one of these equations for every state S. This will give us S number of linear equations, which we can efficiently solve for V pi of S. We define the optimal value function as V star, which is the maximum of all value functions over all policies. If we apply the Bellman equation, this is equivalent to the second equation here. The first term is like before. This is the immediate reward. The second term is the maximum over all actions of the expected future sum of discounted rewards we will get after action A. Let me repeat that. The second term is the maximum over all actions A of the expected future sum of discounted rewards we'll get after action A. So the idea is, okay, I take action A, what's the maximum amount of reward that I can get if I take action A? So it checks all options and produces that. We also define an optimal policy, pi star, like this. This equation gives the action A that attains the maximum in the equation for V star. So this produces an action. Note that pi star has the interesting property that it is the optimal policy for all states. This means that we can use the same policy pi star no matter what the initial state of our Markov decision process. This seems like a lot of math, but don't get weighed down in this. The idea is reinforcement learning problems can be models as Markov decision processes, and there is some optimal way to traverse through actions to receive the best rewards. Now, how do we actually figure out what those are? Well, we need to solve our Markov decision problem with value iteration or policy iteration. Now that we have our Markov decision process set up, we need to solve it. There's two main ways of doing this: value iteration and policy iteration. Remember that we are only considering Markov decision processes with finite states and finite actions. Value iteration and policy iteration are both very simple algorithms. We have pseudocode here. For each state S, we want to initialize the value function with 0. Then we're going to repeat the next loop until we converge. For every state S, we're going to update our value function using the Bellman equation from a few slides ago. This algorithm can be thought of as repeatedly trying to update the estimated value function using the Bellman equations. There are two possible ways of performing the updates in the inner loop of the algorithm. In the first, we can compute the new values for V of S for every state S, and then overwrite all the old values with the new values. This is called a synchronous update. Alternatively, we can also perform an asynchronous update. Here, we would loop over the states in some order, updating the values one at a time. Under either synchronous or asynchronous updates, it can be shown that the value iteration will cause V to converge to V star. Having found V star, we can then use our previous equation to find the optimal policy pi. Policy iteration is like this. First, we initialize the policy randomly, and then we repeat the following until convergence. We let our current value function be the value function described by our current pi. And then for each state S, we calculate the action using our equation from a couple slides ago. The inner loop repeatedly computes the value function for the current policy, and then it updates the policy using the current value function. The policy pi found in this step is also called the policy that is greedy with respect to V. Note that this step can be done via solving Bellman's equations, which in the case of a fixed policy is just a set of S linear equations in S variables. After at most a finite number of iterations of this algorithm, V will converge to V star, and pi will converge to pi star. Both value iteration and policy iteration are standard algorithms for solving Markov decision processes, and there isn't currently a universal agreement over which algorithm is better. For small Markov decision processes, policy iteration is often very fast and converges with very few iterations. However, for Markov decision processes with large state spaces, solving for V pi explicitly would involve solving a large system of linear equations and could be difficult. In these problems, value iteration may be preferred. For this reason, in practice, value iteration seems to be used more often than policy iteration. So far, we've discussed Markov decision processes and algorithms for MDPs, assuming that the state transition probabilities and rewards are known. In many realistic problems, we're not given state transition probabilities and rewards explicitly, but we must estimate them from the data. Usually, the states S, the actions A, and the discount factor gamma are known. For example, suppose that for the inverted pendulum problem, we had a number of trials in our Markov decision process that go like this. Here, S0 to the 1 means the starting state for our first trial, and A01 means the first action we took for our first trial. And so here it's the starting state for our second trial, starting action for our second trial. In practice, each of these trials might be run until the MDP terminates, such as if the pole falls over, or it might be run for some large but finite number of time steps. Given this experience in the MDP consisting of a number of trials, we can then easily derive maximum likelihood estimates for the state transition probabilities. Maximum likelihood estimates sounds really fancy, but all it is really just taking averages, looking at the number of times something happened and dividing by the number of times something could have happened. So we can do that to estimate our transition probabilities. We can see the number of times we took action A in state S and got to S prime, and we can divide that by the number of times we took action A in state S. That is the total number of times we took action A in state S, and maybe we transitioned somewhere else. Sometimes we might have a situation where we have 0 over 0. That corresponds to the case of never having taken action A in state S before. Then we might just simply estimate P of SA S prime to be 1 over the length of S. That is, we're going to estimate the probability when we don't have one to be the uniform distribution over all states. Note that if we gain more experience, that is, we observe more trials in the MDP, there is an efficient way to update our estimated state transition probabilities using the new experience. Specifically, instead of keeping this number, if we keep the numerator and the denominator in this equation in memory, then as we observe more trials, we can simply keep accumulating these counts, computing the ratio of these counts, then given our estimate of PSA. Using a similar procedure, if R is unknown, we can also pick our estimate for the expected immediate reward R of S in state S to be the average reward observed in state S. That is the sum over all observed rewards in state S divided by the number of times we were in state S. Having learned a model for the MDP, we can then either use value iteration or policy iteration to solve for the MDP using the estimated transition probabilities and rewards. So this is a real-world situation where we have the states, the actions, and the discount factor. We can estimate the transition probabilities and the reward, and then we can solve our MDP using value or policy iteration. This video covered reinforcement learning. We started by talking about reinforcement learning as a Markov decision process, and then we discussed value and policy iteration as means of solving our MDP. And then we discussed real-world problems where we have to estimate the reward and the transition probabilities in order to learn the model. The next topic will cover learning theory.